we are going to start with me introducing Andrei Sapera. He's our co-host today, and he's also the Marketing and Business Development Space Application Service, MVSA. So Andrei is going to give us a quick introduction of what IceCubes is and a little bit more background about this webinar. So welcome, Andrei.
Thank you. So I won't take too much of your time because the stage and the spotlight belong to the guest speakers. But I wanted to provide you with a little bit of context and just a brief introduction to the IceCubes service. So IceCubes is part of a larger story called Space Application Services, a Belgian company established almost 4 decades ago with headquarters in Zaventem and also a subsidiary in the US called Aerospace Applications North America. And the service, the IceCubes service, was let's say officially established around 7 years ago when we launched our facility to the ISS. So this was born under a public-private partnership with ESA, and so we've been operational for more than 7 years now, in which we've flown and implemented over 40 missions, including that means payloads, various devices, and also a variety of experiments on board the station. We've been involved in 4 private astronaut missions so far, and we have customers from all around the world. And in the image here, you can see the IceCubes Mission Control Center in Zaventem, from where our operations people monitor and control the payloads. In a nutshell, the IceCubes facility is accommodated inside the Columbus module of the ISS, and that is for the home in space for your payloads, for the payloads of our customers, of our partners. We provide easy access, fast track, and regular access to the ISS, and we fly with almost every resupply mission. And we provide a wide range of capabilities and expertise, and I will show you in a moment what that means. The facility is a simple. We simplified because it's as a commercial service, it's a plug and play, has a plug and play approach. So once the payloads get on board the station, an astronaut basically plugs it in the facility, and from now on, our people on ground take over the activity. And the customers get real-time connectivity from their lab or from their office with their payload for monitoring and for assessment in the quick real time almost. It's not just a platform or a destination, it's also an end-to-end service, meaning that because we want to make microgravity more accessible and easy to use for people for non-space people and for research topics outside the space sector, then we provide this whole journey basically, so we can accompany our customers from the very beginning, from the very first sketches and identifying the most suitable setup, and all the way through mission implementation. So I told you, and you saw the image, we have our own mission control center, so we provide through this infrastructure all the tools and all the means necessary for the customer to have a complete experience and a whole journey to space. So we can take care of all those complicated things, all the certifications and testing and getting all the approvals and booking the flight, etc. So we say it's an end-to-end service in the true meaning of the phrase, but it's also perhaps you want to build a hardware yourself and you need support with other segments of this process. So that's why we say it's a la carte. So it really depends. It's a flexible approach, and it really depends on your needs when it comes to flying experiments to space. I will not go through all of these, but just to show you just a snapshot of the variety of projects that we've been flying and what's possible, because every payload is most payloads are quite different. So you will see payloads and assets that are meant to investigate different topics within the life sciences, but also tech demonstration and physics and cybersecurity, and also educational and artistic payloads and activities. So again, this is just a part of the gallery. You'll see many more images in a few moments. We develop customized, tailored payloads, but we also fly. We have a number of assets that we're flying in a recurring matter, including the Kirara incubator, which is in partnership with JAMS, a Japanese company. So we've flown Kirara 6 times already, and it's meant for protein crystallization, but it can also accommodate various other types of samples. And you'll hear a very interesting use case in a few moments. The Science Cube is actually an in-house development. We wanted something that is simple, flexible, and ready to use for a variety of samples. And you will actually hear 2 stories here because Joseph Borg is here to talk about the missions, and you will also have Dr. Gada to talk about the aging and microgravity, her 2 missions. And a more, let's say, more peculiar asset is hosted all the time on the ISS. It's a media set, and with this we provide live events with the crew, with an audience on ground. So we've enabled almost 100 events during the Axiom missions, and this there's a variety of events that can be done, including interviews and conversation with schools. So and this is all possible because of the system and the infrastructure that we have in place. So apart from this, we're also involved in larger projects such as Astrocardia, which is meant to develop a heart organ on chip for studying cardiac aging in space. I invite you to check out the websites of Astrocardia and also Pulse, which aims to develop a magnetoacoustic 3D bioprinter for microgravity, as well as M4PM, which is a project in collaboration with ESA, aiming to grow tumors, organoids, and spheroids in space. To learn more about our missions and the stories, I invite you to explore our journal, where we write about these projects and the payloads and the assets that are being utilized. And I will pause here because I want to leave the stage to the first speaker, and I will be back with some surprises after the presentations. Thank you very much.
Thank you, Andrei. Appreciate it. And the idea is that we're going to talk today because you presented a very specific set of offering, and then sometimes people ask like, well, what can I do with it? Like, it sounds great, and then we're going to have today some experiences from people who actually translate that into an experiment back at their lab. So let me introduce our first speaker for today, Professor Gada Al-Saleh. She's trained as pharmacist before following her ambition to become a scientific researcher. She established her own research group at Botnar Research Center at the University of Oxford, where she is investigating how controlling autophagy can intervene in biological aging and age-related diseases. And more recently, she achieved a significant milestone by establishing the United Kingdom's inaugural Space Innovation Lab at the Botnar Institute for Musculoskeletal Sciences, again, also in Oxford. So thank you so much, Professor Al-Saleh.
Well, thank you so much, first of all, for this introduction and also for having me here. It's really a pleasure to be here. And as you mentioned, actually, my research focused on understanding the mechanism of aging, immune senescence, and mainly cellular hemostasis. And I think I'm going to talk to you a little bit more, actually, though briefly, because we don't have that much of time, about our recent experiment to understand aging and using microgravity, the mission called Aging Under Microgravity. The aim of this mission is to address the growing challenge of the increased aging population in the world. You can see here in this card that actually people live more than 85 years old, and this is really different in different countries. Of course, this is an amazing achievement. The issue here that this actually coming with increased comorbidity with different age-related disease, and we even can see that these people, elderly, might have a different complication, not only one. Some of them even can go for 8 disorder. Of course, these people will have definitely different polypharmacy, different drug that have never been tested correctly before, and also we never include the aging population in our cohorts when we study a new drug. And this is what make actually most likely the cost and the issue in the economy related to the increase of age population. And in my research, I really wanted to look into a model that could accelerate our research to understand the aging process and how we could go faster. And one of these models that we definitely can help us and give us a very unique environment is actually the space. As you all know, that the astronauts actually have a different disorder when they go to the International Space Station. They do suffer from muscles atrophy, they lose their bone, and also they have a bit of complication in their immune system. And if we look at their life, daily life, they already have a different day. At least they have 15 days and night in our one day. So they have the one cycle in 1 hour and a half. And this is definitely have a huge implication in their biological process and also their biological clock and many others. So we thought, can we use this? Can we consider that this process that happened in space is exactly the same that happened in Earth? Can we identify shared biological pathway between aging and the space flights? And this definitely will help us to protect the astronaut in their and during their mission, especially now we think to go for a long mission. But more important, we would like to help people who grows and become elderly and suffer from different age-related disease in Earth. And we do really hope to identify maybe new biomarker or even identify drug that could target and improve how we test the drug and how we actually could go around the aging mechanistic that happened in Earth and also in space. So to do that, and to be able actually to go into our goals, one of the main things that we were managed to do is to establish the Space Innovation Lab. This have been done in collaboration with different collaborator, Metaspace and definitely Space Application and IceCube with ESA and NASA. And this is a platform, as Andrea just mentioned before, it's really a breakthrough technology, because from my office, and maybe you can see it just behind me, we are able to control the sample independent of the involvement of the astronaut. So this really saves the cost and the time, because as you know, if you want to ask astronauts to be involved, then you have to train them, you have to tell them what kind of experiment you definitely need. And in this case, we don't really need their involvement. And the other things we definitely could control the sample, having the data 7 days, 24 hours every second. So this is really amazing. And to continue in that, we wanted to, when we want to send our first experiment, as I mentioned before, it's called Aging Under Microgravity, and maybe you appreciate and see here, this is the sample of this mission. What we do, we prepared different 3D organoids. We actually prepared 120 organoids, 60 we sent them to the International Space Station, and the other 16 have been stay in Earth. These organoids are different, some of them coming from human synovial from the joint of people who suffer from osteoarthritis disease. We do also have some organoid where we take cells from human dermal fibroblast. And I just want to show you here in this image how these 3D organoids look like, and I want to just to appreciate the blood vessels and also how the cells were actually forming in the cells. And the other image is even more clear, where we were able really to produce these vessels into this specific organoid. And this is something a very little challenging and take us really a little bit of time to be able to have organoid that mimic the human tissue. And this is very important because, as you know, we can't take a sample or tissue from the astronaut from all the tissue, right? Like we could get some blood or others, but if we want to have a synovial tissue which coming from their joint or even the liver or the heart, that would be really challenging. So developing this 3D organoid that mimic our organ is something very important. So we're very excited that we managed to do that. And now I'm going to just give you about more the excitement and some of the challenge that we have in this process. These are the two people from my lab. Here is Declan, who was a PhD student. He was very excited because in her first week where he arrived to the lab, he had to go and fly to NASA to do the experiment alongside with Vincent, who was a postdoc in the lab. So definitely we take all our materials, so we have to think exactly what we need, so we can't really forget anything, because it would be very hard to send it from UK to America in the meantime. They prepare all this organoid. This is a photo where they were doing that. This is when we finish. This is, of course, the ice cube model that we use in this mission. We were most likely managed to set up, not to change the media, but we were able to have an image in a time rail. And this is a sample. Of course, this is really very exciting moments, which I can't really express my feeling about it. This is the day when the lunch have been done. So they were invited alongside, of course, with Luca, who's coming from a space application, to see the lunch while we were in the lab, talking to them here in the phone to see what has happened around us. This is just to show you the next day. Of course, we were looking into the docking, and definitely the astronaut take them just 2 minutes of their time just to take this box and plug it into the International Space Station. You know, so this didn't really need any training, as I mentioned before, and this is also another photo. We were very happy to see the cube flight and also have been settled well in the ISS. And from our lab, we could control the temperature and the image. So this is a live image at that point, and you can see another one just behind me for all the organoids in these different cube. And we can follow them and we can see what's going on in the time rail. Of course, the sample went back to Earth. So this was the most recompense for us after all this work. And we were very happy to see that they were still alive. They look very nice. I mean, one of them, I always look at it as it has become an extra interest organoid, but it's really nice. And it's very early for me to tell you what is the data. However, really our primary or first data look very promising. So we might be able really to answer the question that we were looking for. That's it from my side. I'm more than happy to answer any question about this mission. And thank you again for having me with you.
Thank you so much, Professor. Thank you. We appreciate it. And I think we have many questions. I invite everybody to put them on the chat. All the participants are going to present our next speaker, Stefano Seriani, Associate Professor of the University of Trieste.
Hi, my name is Stefano Seriani. I am Associate Professor of Robotics at the University of Trieste. My main area of research is space robotics, and I am the principal investigator for the RISE experiment that is on board of the International Space Station since November of last year. Our experiment is about the integration of electronics in 3D printed satellites. The goal is to develop technologies to modularize space components, to make them easier to assemble and reduce their overall complexity. With this project, we aim at understanding whether the integration of electronics directly into 3D printed components is a viable option and how it compares to traditional methodologies. The space environment found on the ISS plays a significant role, but in our case, the main aspect of the endeavor was to validate the entire process, from design on the ground through testing and launch, finally to commissioning on the space station. In orbit, we gathered millions of data points that are now enabling us to discover how and why our technology has proven to be successful. Fault detection, embedded sensor monitoring, and so on are many of the aspects that were tested. As a personal reflection, I believe that as a people, we need to take care of what we have, but also to push the boundaries. Space is the next frontier. It is where most future opportunities lay, and anything that contributes to this goal fascinates and motivates me. However, as the saying goes, space is hard. And I got to really experience that, all with the grueling work that led us to finally being able to launch on the ISS last November. So the RISE tech demo, you can see here, this is a mock-up, is a 10 by 10 centimeter cube designed and developed here at the University of Trieste with the help of PicoSats. Most of the electronics is custom built, except for the onboard computer, which is an inexpensive Raspberry Pi. The cube structure is entirely made of a very high performance 3D printed polymer, which we printed in-house. The Ice Cubes team was phenomenal during the entire project. Big shout out to all of them. They supported all of our planned activities and dealt with the unplanned activities as well, all with good responsiveness and coordination. They supported us through a lot of the phases of the project and of the mission, design, testing, and during the flight. For the future, we have many ideas indeed, and many are a direct consequence of the experience with Ice Cubes. The infrastructure the Ice Cubes team has put into place did in the end make working with a space asset almost easy. And this is not a minor feat. We are currently working on a sort of scaled-up version of the RISE project, but with other applications in mind. Think about 10 to 50 times its size. This is part of the Realize 2 project funded by ESA, which started 2 months ago. And this deals with the assembly of very large structures directly in orbit with robots. Thank you. It's been a pleasure.
That was Stefano Seriani. And we're going to keep moving along because we have still a couple of very interesting speakers. I'm going to introduce now Professor Elena Kozlova. She's the professor of regenerative neurobiology department of neuroscience at the Uppsala University. Her research profile is basic and translational research aimed at developing novel treatment strategies for spinal cord injury and disease. And now the microphone is all yours, Professor Kozlova.
Good afternoon, everyone. Very nice to be here. Unfortunately, I don't see anybody and anyone, even just my presentation. I will try to make it for 6 minutes. We work with BC. It is abbreviation for cells, which we call boundary cap. They are sitting in the transitional zone. It's a boundary between the spinal cord and peripheral nerves. These cells we can collect from embryo and then grow them like neurospheres. So the cells called boundary cap, they are located, this is yellow cells, on the boundary between the spinal cord and nerves. We can collect them and grow like neurospheres. These cells, this is a neurosphere collected from this embryo. And if we start to differentiate the cells, we remove stem cell medium, they produce neurons and glial cells. Neurons here red and glial cells green. Why we need these cells is because during traffic accidents or when patient fell from the bike, these nerves are just ruptured out from the spinal cord and they never grow back. If we place these stem cells in this area, the nerves can regenerate, function will recover, and patient will not have neuropathic pain. We found another interesting feature of these cells. If they will be placed together with pancreatic islets, and this is small parts of our body where we have cells producing insulin. These insulin-producing cells never proliferate, never divide. but if they place together with boundary cup, they start to proliferate. And here you can see a lot of red cells. They're proliferating because of presence of boundary cup. The BC also very good in 3D printing. You can see them here. They are 3D printed. They survive for many weeks, and they also produce neurons and glial cells in the scaffold. In 2019, we had an opportunity to place them to sound in rocket to experience 5-6 minutes of microgravity to see if they can survive and for how many days they can survive without medium change and in closed epindors. The cells successfully came back. They've been sent either like neurospheres or 3D printed neurospheres. And we found that if the cells will be placed into medium to differentiate, they again produce neurons and glial cells. But they've changed very much. Here you can see the first column, it's cells which have been in space. This is their genetic changes. Compared to all the three other columns, it's ground controls. So some change happened, and we saw that the cells were very quickly proliferating compared to other cells, and they were able to produce other type of cells. Here we have fat cells, only from space cells, but not from the control cells on the ground. It means that they also got a capacity to produce some other cells. We were interested if it is due to microgravity or due to hypergravity. So on the next experiment with sound in rocket, we placed a centrifuge, which as soon as cells reach the microgravity condition, part of them were starting centrifuge rotation with 1G, so they avoided microgravity. To addition to BC, we also took these pancreatic islets to see if microgravity will induce their proliferation. And this is a centrifuge. This is where our cells have been placed, and this was placed into rocket in a late access unit. The cells will be as fresh as possible. You can see here, this is pancreatic islets, and this is our BC. They proliferate very happily in the space and even remind some plane. We also noted that pancreatic islets also proliferate, but it happens only 2 weeks after landing. By this experiment, we found that effect from microgravity can be some time delayed. It will be not detected directly after microgravity experiment, but several weeks later. So it affects now our protocols for future experiments. In January 2024, we have been able, with the help of IceCube, to send cells with a Swedish cosmonaut Marcus Wand to International Space Station. The experiment calls MEMO-BC because it was boundary cup which already have been in space 1, 2 times or never been in space. We wanted to compare how they will be affected by this long exposure of microgravity. They also been 3D printed or in free form, placed in these cuvettes, and then located into this IceCube produced box. And we've been also in Kennedy Space Station to prepare cells that they will be as fresh as possible. And here you can see Leonardo, who was very helpful. And this picture shows that Marcus Wand did not forget them, and he really had them on International Space Station. So what we learned, the experiment, as many of you maybe remember, was delayed, and cells exceeded the period of expected survival, because maximum what we knew they can survive it is for 3 weeks without medium change, but it was 25 days. However, slowly proliferating cells survived, and we were able to restore these cultures. And we saw that cells in 3D printed form survived much better, and they were proliferating effectively. However, these slowly proliferating cells were still able to produce neurons and glial cells, and we tested them with electrophysiological methods and show that they are absolutely normal, but their metabolomics was changed. Here you can see that cells from space have been completely different from ground control cells, and when we tested other space cells from sounding rockets, they all been different compared to ground control, which shows that some features of cells which are received from the space exposure are stay forever. So our conclusion were that you really need very dedicated people. You need a very good coordination in the team, and you have to be ready that you will have much more questions than answers from your experiment, and you have to try to go to another experiment, even if it will take several years for preparation. And the main, what I learned from this last experiment, that you should not give up and on your experiment and see what actually will happen. Like in our case, when we almost didn't expect any success, but we pushing this limit and we made one step beyond and found a new very interesting insights, because these slowly proliferating cells, they're cells which survive. And we know that cells proliferating very fast by seeing the DNA in samples from space and ground. But for some reason, only slowly proliferating cells survived. So we think it could be very interesting for even cancer research and other areas in science. So we are working now on this. And this is our group. And people who've been helping us to have these experiments is, of course, ESA, it's IceCube, a Swedish Space Corporation. Then there is a lot of collaboration with Italy, USA, Belgium, it's Marcel Egli from Switzerland, and we have support, financial support from Swedish Space Agency. Thank you.
Thank you.
Okay.
Thank you so much. And now our next speaker also sent a video, and she's now here in the audience ready for the Q&A if you have any questions for her. That's Professor Petra Bombish. She is the head of a research laboratory at a Research Center for Natural Science in Budapest.
Greetings to everyone. Thanks for listening. My name is Petra Bombic. I am the head of the Chemical Crystallography Research Laboratory in the Center for Structural Science of the Research Center for Natural Sciences, Budapest, Hungary. Our goal is to develop a method for single crystal growth of organic compounds in microgravity. There are several examples of protein inorganic compounds crystallization in space, but single crystal growth of organic compounds is not yet in practice. The participants of the project are the Space Application Services, IceCube Service, the Japan Manned Space System with Confocal Science Corporation, and the Hungarian To Orbit program. Our samples flew to the space in the frame of the Kirara 6 experiment carried by the SpaceX 32 cargo mission. The launch was on the 21st of April, and the samples arrived back to Earth after 35 days from the International Space Station. Here is the IceCube on board the ISS. We expect to achieve better crystal quality in space for single crystal X-ray diffraction structure determination. To get crystals with improved internal arrangement, crystals which are more unidimensional and larger in size. As there is no sedimentation or buoyancy in microgravity, the diffusion becomes superior to convection. The speed of the crystal growth is suppressed. It makes possible crystal structure determination with higher accuracy. It contributes to understanding the relationship between molecular structure and macroscopic properties to be able to control the self-assembly of the molecules. We intend to grow single crystals of highly ordered porous architectures, so-called hydrogen-bonded organic framework materials. They can be used for molecular storage, for separation of chemicals, or as catalysts. There are limitations working at the ISS. The payload is very limited. The IceCube is thermostated, no way of crystallization by temperature change, although solubility depends on temperature. Safety precautions are strict, which influences the selection of the solvents and tools. There is no human intervention in space, and vibration is a risk. Our great challenge was timing. The experimental setup was completed some days prior to the launch, but crystallization had to be started on board and not before. It is a vapor absorption method we developed for single crystal growth using the CSGT container received from the Japan Manned Space System. The method worked well. Nice single crystal was grown on orbit from one of our two compounds. The single crystal X-ray diffraction measurements were performed at the diamond light source. The structure evaluation, analysis and comparison with the ground-grown crystal is in progress. The logistics of the transportation of the sample was also a challenge. While the sample traveled approximately 40,000 km on Earth in gravity by plane, the space station is only 420 km away from the Earth. The crystals are fragile, they easily decompose. We are very grateful to Space Application Services for involving us in this project and for the way they followed the project development step by step. We are very grateful to Japan Manned Space System for guiding us during the method development, teaching us about the working condition at the ISS, and conducting the reproduction experiments. The communication, the support and the guidance of the two partners from Europe and Asia were excellent as a dream during the entire project. Finally, I would like to acknowledge my colleagues who are working on the project and thank you for your attention.
So let me introduce our last speaker before we move into the Q&A, Professor Joseph Borg. He's a molecular biologist and space bioscience researcher at the University of Malta and also founder of Space Omics. His work bridges genetics, omics, and spaceflight, leading groundbreaking biomedical research on board the ISS. And he has flown many, many times. And so it's going to be very interesting to hear as well his experience. So, Professor, over to you.
Thank you very much, Jose, and for your team in organizing these postcards from space. I mean, I was very, happy and excited when I received the email to join the group. So thank you for the initiative. Yes, indeed. So, I mean, I've tried to keep a small number of slides just to grab the essence of the importance and usefulness of sending experiments to space, and most notably using the IceCubes facility on board the space station. So what you see here in the front screen is one typical science cube or ice cube as we know it that we have used to send our first set of experiments on board the space station. So we've sent a total of 3 ice cubes to the ISS, and these were sent in consecutive years. So starting in 2021 on SpaceX CRS-23, and this was handled by French astronaut Thomas Pesquet. And this was our first time where we sent human skin tissue samples and specifically human skin microbiomes. So as you know, life and humans are full of bacteria and microbiomes, which includes oral, gut, but also on skin. So we have been looking at skin microbiota on healthy adults or normal people and those who unfortunately have ulcers or foot ulcers as a complication of diabetes type 2. And we wanted to see the effects of spaceflight, radiation, and microgravity, and the effect on these microbiomes. And for our main objective here is to see how the bacteria behave, adapt, grow, etc., and what this can in turn allow us to understand how to devise better treatments. As most of you know, with every passing year, there's an increase, risk or urgency with antimicrobial resistance, and patients or people with foot ulcers and other infections as complications are running out of options or medicines. And unfortunately, in the case of diabetes, these patients end up with minor amputees of the toes, orals of the foot, or below the knee. So it is a very serious complication. A year later, the same ice cube but it was a slightly upgraded form because instead of a 3D printed ice cube, it was the machined aluminium ice cube. And this was handled by Italian astronaut Samantha Cristoforetti. And here again, so we always have around 6 samples on board the ice cube, and the other parts of the ice cube, as you've heard before, consists of electronics. So these includes cameras, includes the Raspberry Pi computer, and includes the necessary electronics for us from Earth to space to be able to connect and switch on the camera, take photos, videos, and also download any important telemetry. And finally, the third and final mission in CRS-27, it was handled by Emirati astronaut Sultan Al-Nayadi. This was the culmination of our final mission in this program. We call this the Mallet project, or the Mallet trilogy. So we have 3 missions in total. And in this mission, it was interesting because for the first time, we also had Maltese patients, but also Saudi patients from King Faisal Specialist Hospital in collaboration with Dr. Badr Shirah. So we also have some interesting collaboration that transcends borders. Of course, science is nothing without publication and showing out there what it really means. So in fact, as a first results or publication from this program, we have the very first set of data and results from the first space mission done in 2021. So at this time, so this paper shows the data from the first mission in 2021. So right now, and it is almost complete, we have the full results analyzed and data analyses from the second and third Mallet missions. And we are now hoping to publish a follow-up study, which is a more comprehensive study that looks at the shifting of the microbiome in space versus Earth. So these were 3 very exciting missions. And I really enjoy working with space applications and ice cubes because through this work, I also learned a lot and also met other colleagues back in the States and Canada and elsewhere. And through them, we also got to test and analyze blood samples of astronauts. So these included astronauts from NASA, the NASA twins, Mark and Scott Kelly, NASA astronauts from JAXA, from Japan, and also private and commercial astronauts from SpaceX. So largely we have touched with Inspiration 4, Polaris Dawn, and Fram2 this year. So most of my work, so now this deviates a little bit from the ice cubes per se, but it will come back full circle. I will explain why. So last year, 2024, and also some of the previous years, so we worked also with blood science. Our primary aim was to see the effects on blood and erythropoiesis and the development of red cells in human astronauts. And as we know, there are some forms of complications related to anemia. This might not be hugely of an issue on board the space station, but if and when humans will venture forth to the moon and deeper space, anemia is a real problem, and blood is something that we have to take care of in earnest. We have also published a very important study in Nature Communications, and the reference I've shown down below, which shows the shift that blood in humans in space sort of preferentially shifts to the more primitive and embryonic and fetal type of erythropoiesis. Why do I say full circle? Because in one of these missions in Fram2, so this year, so besides working with blood and taking blood samples of astronauts, we also gave these astronauts payloads to take with them to space. Now, these were not ice cubes missions to the space station for 30 days or more, but these were very short duration missions of 3 days, 4 days. But nevertheless, the ice cubes per se serve their purpose as passive payloads in these missions. And in fact, in our last mission, these ice cubes also serve the purpose again to carry for us erythropoietic stem cells, peripheral blood, cord blood, bone marrow stem cells, and various other blood cell lines. Of course, this is not the same as growing these cells in a cell culture facility or lab. However, we had our modifications and updates. We made use of CO2 independent media, and also kind of media that allows the cells to remain viable and alive even at ambient temperature and not necessarily at 37 degrees. So this was something that we could sort of work around using the system within the ice cube infrastructure or hardware, so to say. And of course, we always compare with ground controls kept at the same conditions precisely. Very interestingly and excitedly for us, one of these payloads was also supported by scientists in Saudi Arabia. Here I mentioned Ayub Al-Subehi, and we looked very specifically at the ocular microbiome of selected individuals from Saudi Arabia. So this was a small pilot study, and we are hoping to grow the study into many hundreds of patients by looking at this very niche and important microbiome of our human or human life, so to say, right? And this serves a very important part for those irritating or very fastidious infections that astronauts might encounter on the eye or just in the conjunctiva during space missions, etc. Yes, and this I conclude with a small video. I hope you can see the video. So this was the actual ice cubes back in space this year, free flying in microgravity. Small comment. So these ice cubes actually went. So Fram2, if you don't know, was a world first polar mission to the Earth's orbit, so from north to south, and it contained, of course, 4 astronauts, one of which was a Maltese citizen as well. So we can say that the ice cubes also went on a world first polar orbit mission from north to south. So that brings an end to my set of small slides, and of course I remain very happy to answer any comments or questions you might have. Thank you, Jose, and thank you all the team.
Thank you so much, Professor, and great video. That was a beautiful, beautiful photo. Yeah. So now Andrei has a little treat for us. And right after that, we're going to go to the Q&A.
I mean, it's not called postcards from space for nothing. We actually have some postcards from space, so this was my little surprise. So we will actually start with a postcard from ground. So these are images from the handover of the first Aging Beyond Earth mission that Gada told you about. This is a collage that we prepared with some images that actually came from the ISS. So this is the second mission of Oxford, Aging Beyond Earth, using the Science Cube, the upgraded Science Cube. And you heard a little bit about the story earlier from Dr. Gada. And this is the postcard dedicated to the RISE cube that Stefano talked about during his recorded video. You will see the cube in our ICF on ground, but also in the middle you'll see this medallion floating inside the cube. So the payload was a half engineering, like technology demonstration, and also it had this let's say inspirational side dimension, and then also an image from the ISS with the cube installed in the ICF on the ISS. And here we have a nice collage of MemoBC, so you can see the group right before handing over the payload, and on the right side you see Marcus with holding. He's not holding it, but the MemoBC box floating. And this is the Kirara 6. This is the research of Dr. Petra Bombic, who also provided us with a very, very nice video. So this is the dedicated postcard from space. And finally, the Maleth trilogy postcard from space. So the 3 Maleth projects that Dr. Josef Borg talked about. And yeah, let's have a conversation. So I will stop with the postcards. Well, I will keep the postcards so you can look at them, but let's kick off the Q&A.
While we get ready, I wanted to ask all the speakers, what was the most unexpected thing that happened during your project, both in a positive and negative, which is also important.
Well, I can come with something. Actually, it's really happened to us, which was unexpected. That the lunch had been changed. It was like for the weather, and there was a lot of change at that moment. So the launch day have been changed or moved for 2 weeks or something like that.
That's
It is okay, but the problem was we have definitely to send again all the sample, all the human tissue, and all the organoid that we prepared for the mission. We have to replicate that. So at the moment, we were really, really very, like, stressful, but we managed. So that's what negative, but we managed to go around that.
Can I ask you where you've been located in this moment when you had to wait, at home or in Florida?
No, actually, I was here in the lab, but my students were already at the Kennedy Space Center, and they prepare all the organoid because we need at least 10 days before the launch. So they have already started the process and used everything, and then it just like 2 days before, or I don't remember exactly, like a few days before, they said, "Oh, for the weather, we can't actually do the launch, and it won't be happen before 2 weeks minimum."
But your team, they've been in Oxford or they've been in
No,
United
they were at the
States?
Kennedy Space Center because they were ready to send the sample for launch.
Yeah,
So
I can imagine.
Yeah.
I think something which is, how to say, very peculiar, I would say, Jose, was the fact that myself and my team, we worked on this small payload for the first time, the very first one, right, in 2021. And we came to Belgium, Brussels. And it's like there's this very, very strange and funny feeling when you have the full integration of the payload, and then that's it. So the payload is in the cube, in the how do you say, in the black box, and it is shipped to the States. So in this case, in the first missions, or for most of Malet missions, so we were not physically present, right? Like you are not exactly there, and you do not know about the handover process from Kennedy Space Center to SpaceX or astronauts. So it's like, what happens next? When will I see the cube? So only a few days later. So you have to wait a number of days until the teams at IceCubes and at ESA, they show you the footage of the cube in space and being assembled on site. And it is one of the most beautiful, how to say, feelings or things to see for the first time, to see it true, right? Because it is almost unbelievable at first, but it is true. And so a lot of thanks to all those people who actually handle and do the work also as part of the mission for us. So there has to be a strong element of trust and collaboration, right?
Right.
That is great. Thank you for that answer. And Andrei, I think you have a question for you about the thermal control on the IceCube.
So yes, that can be implemented. I mean, one of the cubes we've flown with the Oxford samples. So the upgraded version of the Science Cube does have heating, basically, so that we can keep the cells at around 37 degrees.
There's another question. Does IceCube have a platform for organ on chips?
We are working on it. So yes, I think if there's interest in this, we can have a conversation. So it's one of the projects that I mentioned, and we are working on more than one solution for this kind of research.
Thank you for that. I have also a question for the speakers. There's some people that it might be their first time thinking about space, and so what would you say to these people?
What would be my message for new for people who preparing this for first time? Actually, I had on last slide, but I was really trying to make it in 5 minutes. Maybe I went too fast, but my last slide was exactly how to say, putting all our experience, which could be, I think, useful for people. No, I think it's the main thing is to have a very strong group with a very big trust, how mentioned another speaker, because it's very stressful. As again mentioned another speaker, it could be very stressful, and you really need support from your team, and also that you shouldn't give up, because it was when our cells exceeded the limit of the survival time, it was suggested just to forget about this box, and I was myself ready to go back because we were very tired and sick, and we still decided to wait, and we very happy to get this support in right time, because we received very interesting results which we think could be useful for researchers. So never give up, and don't be afraid to go above the limits, because this is where you can find something interesting what you don't expect. And be ready that it will be more questions than answers from your first experiment in space, and so try to prepare for the next experiment, even if it will not be very soon.
Thank you, Professor. Thank you. And Professor Petra Bombic, I thank you for your video and thank you for joining us. I know you are with limited access to internet, so we appreciate it. Anything else you have to add to your video and also to the question in place? I think you're muted.
Okay.
There you go.
So there was a question about the most unexpected event that happened. And first of all, I would say the invitation to work at the ISS, it was a big surprise and a big honor for us. And we enjoyed all the moment, and it went very, very, very smoothly, the whole process, about a year for the preparation of the experiment. And there was a question about thermostation. Yes, the ice cube was thermostated to 20 centigrade, and we prepared, we optimized our experiment being performed at 20 centigrade. And some days before the launch, we were told that it may happen that for 24 hours, there is no thermostation during the packaging of the capsule. And then I started to worry about it, because the experiment was optimized to 20 centigrade, but finally it didn't happen. So it was one thing, that there are several things that you cannot foresee at a launch, at an experiment at the ISS, but finally everything went really very smoothly and we got the crystal.
Great, thank you for that. I'm gonna now ask Professor Gada, and then I'll finish with Joseph, because Joseph has another question coming as well. So what message would you provide, Professor Gada?
I think that Professor Elena really mentioned it all, that we do have to be resilient. We have to be prepared for the, any surprise, and we should not give up. But the other things, maybe I just want to add that now with all the development, actually space experiments are more available. I think at some point you did mention the cost, and with what we have now, the costs have definitely reduced at least 50% of what have been like an experiment you would like to do 5 years ago. So it is really open to anyone have a good idea. It would be possible. And again, I think we are doing a great job with space applications. So also to go back to these two questions about the temperature, or about organ on chip, or about like when we put or stop the experiment, there is a lot of things happening now. We developed with the space application to have this biological coop where you could even fix your cells while they are in the space station. You can change media, you can do so many things. So the idea here, there is a lot of possibility. Whatever your idea, what is your question is, don't be afraid to ask and see, can we do it? But most important, what is the impact of doing it? So
thank you so much.
May I tell you that I'm very interested with your experiment, and I see how our two experiments can join for very meaningful experiment in space together. If you don't mind, maybe we get in touch after this meeting and discuss it.
Absolutely. And I just want to tell you, like, some of our data shows a little bit what you did already mention, you know, like a high proliferation, and then if few cells were slow, they come back. So it's yeah, absolutely. We should go for it.
Okay, very good. See you soon.
See you soon.
Great, great. And finally, Professor Joseph.
Yes, I mean, what is interesting and useful to know is that nowadays, especially not on all social media, but perhaps via LinkedIn or maybe also via publications or articles, right? I've seen that most of the people working in the space and science community are accessible, are good to reach out, and they reach out back, right? So if you have any, whether you are curious, whether you want to be part of an experiment or a mission, I think you will find it very surprising that you would be able to see up close such experiments, even maybe if one or the first try that you send for feedback or to access the labs or etc. might be negative, because some of the laboratories might be how to say, maybe due to the workload or due to the intensity. So not everything happens the first time, but persistence is key. So this is very true in my case. So I mean, I would have never imagined they've sent a first cube with ice cubes, and I would have thought the first time that it sort of stops there. But when I saw the interest of the students, of the government, and of private enterprises here in Malta, also abroad, I said, this is something that we can keep on going. And I mean, we stand today now, 4 years or 5 years later, we've sent 3 small cubes or four cubes to space and back. And not just that, starting with the ice cubes and payloads also opens up parallel or peripheral opportunities as well. And I think that is very, very interesting and useful to young and upcoming students, especially for academic qualifications, degrees, and the like. So that is my message to them. Perseverance is key.
Thank you so much. And I think we have one last question, and I think you might be also the one answering this about the limitations. Go ahead. What are the main limitations of studying the microbiome in space using platforms like ice cubes? And how could they be overcome to better understand microbial behavior in extreme environments?
Of course, a very quick comment is that, first of all, microbiomes, okay, they are various sites. So of course, the oral and the gut kind of microbiomes, it is natural that these are kept to higher temperatures or body temperatures, right? So that might be tricky to use existing, or at least the experiments that we used in ice cubes, because the temperature was not controlled steadily at 37 degrees. But that was our case, because in our case, we made use of microbiomes on skin or human skin, where roughly the microbiomes are subjected to ambient temperatures. In terms of limitations, so microbiomes thrive and grow with their hosts, right? So you cannot really study bacteria on their own, but they need to be part of the host. In our case, we try to overcome the issue, the limitation, by having actual host tissue or human skin tissue from the amputees themselves. So at least the bacteria are still part and parcel of the microenvironment. Of course, you might have seen the very first slides by Andrei. I mean, the ice cubes and the platforms are ever changing. There are also complex kind of microfluidics involved, and some of the limitations involving temperature control, also changing of media or constituents of media. This can also be done. So I think the limitation would be the funding or the money. But with any decent amount of money or funding, you can really do away with a lot of the limitations that one can. It's very important to have ground controls that you are able to do, in our case, for genetics or genomics, to do comparative genomics from space to Earth with ground controls that also are, as much as possible, kept at the same conditions, minus the microgravity and radiation. That's about it, really.
Ray, over to you for some closing remarks.
Some closing remarks. Thank you very much. Thank you all for your responsiveness and for your availability, and thank you to all the speakers that joined to tell their stories. Something tells me that we need to do this again, because there's a lot to talk about and a lot of many stories to share. And also thank you to the audience, to everyone that followed this webinar. As Jose said in the beginning, it is recorded, so we will post it soon if you want to watch it again. So thank you all for all the stories and for all the moments shared with everyone, and I hope you have a great summer.